Good morning, dear students. Today we will start a new chapter, solid state. See, matter on the basis of the forces of attraction between the constituent particles such as atoms, ions or molecules exist in three different physical states, mainly gaseous state, liquid state and solid state. You know that the constituent particles in gases and liquids are held together by relatively weak forces of attraction as compared to those in solids. As a consequence, they can translate, randomly rotate, and vibrate. Gases and liquids thus have the ability to flow and take the shape of their container. On the other hand, the constituent particles in solids are held together by strong forces of attraction. In other words, the constituent particles are closely packed. However, these particles can still vibrate about their fixed mean positions. Solids possess some characteristic properties. They have a definite shape and volume. They lack the ability to flow. They are incompressible and they are rigid. In general, the distinct properties of the three different states can be attributed to the arrangement of the constituent particles. In other words, any change in the arrangement of these constituent particles changes the physical state of a substance. Based on the arrangement of the constituents, solids classified into two categories. They are crystalline solids and amorphous solids. Crystalline solids have an orderly arrangement of their constituent particles such as atoms, ions or molecules in three dimensions. These are arranged in an orderly manner to give a definite geometry to the crystal. Thus, a crystal is defined as a solid figure that has a definite geometrical shape with flat faces and sharp edges. Quartz and sodium chloride are examples of crystalline solids. Now, let's discuss amorphous solids. The term amorphous has been derived from a Greek word or morph, which means shapeless. An amorphous solid consists of a number of constituent particles arranged in a random manner. Hence, amorphous solids do not have any definite geometry. There is a short range order, which means that there is an irregular arrangement of particles that repeats itself to a certain extent only. Glass, rubber and plastics are examples of amorphous solids. In many respects, these solids resemble liquids. They flow very slowly at room temperature and are regarded as a supercooled liquids in which the forces holding the molecules together are so great that the material is rigid but there is no regularity in the structure. The flow of these solids is clearly observed in glass pans fixed to the windows or doors of old buildings. These are found to be slightly thicker at the bottom than at the top. The best example of crystalline solid is quartz, and of amorphous solid is quartz glass. Best arrangement is shown here. From these two images, you can clearly observe that both solids have similar arrangements. However, in quartz glass, there is a short range order, A crystalline solid has a sharp melting point, that is, when it reaches its melting point it immediately changes into liquid form. These are considered true solids. Amorphous solids do not have sharp melting points. This softens over a range of temperature and can be molded and blow into various shapes. The solids behave as crystalline at a certain temperature, and these are considered as a pseudo-solids or supercooled liquids. Crystalline solids are an isotropic in nature. In other words, some physical properties like refractive index and electrical resistance change along with the change in the direction of the property. This is due to the ordered molecular arrangement in the solid state. Amorphous solids are isotropic in nature. In other words, they show the same physical property in all directions. This is due to the random arrangement of the solids. If a crystalline solid is broken into pieces, the small constituents will have the same smooth and plain surfaces. Crystalline solids have a definite heat of fusion values, whereas amorphous solids do not. Another important property of this solid is symmetry. Solids show plane of symmetry, axis of symmetry, and center of symmetry. On the other hand, amorphous solids do not show any symmetry. On the basis of the types of forces holding the constituent particles together, crystalline solids are broadly classified into molecular solids, ionic solids, and metallic solids, and covalent or network solids. Let us begin our discussion with molecular solids. The constituent particles in this type of solids are either atoms or molecules. The atoms or molecules are held together by weak forces of attraction. Further, on the basis of the nature of the intermolecular forces of attraction, molecular solids are divided further into nonpolar molecular solids and polar molecular solids. Hydrogen bonded molecular solids. Okay, so let's discuss each. In nonpolar molecular solids, the constituent particles are either atoms or molecules. The atoms or molecules in these solids are held together by weak dispersion or London forces. As a consequence, these molecules have low melting and boiling points. Hence, most of them are liquids or gases at room temperature and normal atmospheric pressure. For the same reason, they are soft as the electrons remain localized to a particular atoms or bonds. These are non-conductors of electricity. Hydrogen bonded molecular solids like polar molecular solids, the constituent particle molecules are formed by polar covalent bonds. However, the bonded atoms in these molecules are essentially hydrogen and a highly electronegative atom such as a fluorine, oxygen or nitrogen. Ice and solid hydrofluoric acid are two examples of hydrogen bonded molecular solids. The molecules in these solids are held together by strong forces of attraction called hydrogen bonds. As a consequence, the solids have high melting points among the three types of molecular solids. Like the other two types of molecular solids, the solids are also non-conductors of electricity at room temperature and normal atmospheric pressure. These are either soft solids or highly volatile liquids. The other type of crystalline solids is ionic solids. The solids have the ions as their constituent particles. The Coulombic force or electrostatic force of attraction hold the ions together, that is cations and anions in the crystal. These cations and anions arranged regularly in three-dimensional space to form ionic solids such as sodium chloride, cesium chloride and zinc chloride sulfide. These solids have high melting and boiling points. This is attributed to the strong electrostatic forces of attraction. As a result, these solids are also hard but brittle. As the ions are in fixed positions, they are non-conductors of electricity in solid state. However, they are good conductors of electricity in fused or molten state. Metallic solids. In metallic solids, the metal atoms such as copper, iron, silver and magnesium lose their valence electrons to the crystal as a whole. These solids are merely a collection of positive ions surrounded by and held together by sea of electrons. Hence, the constituent particles in a metallic solid are positive ions in a sea of delocalized electrons. The electrostatic force of attraction between the positive ions and the electron cloud constitute the metallic bonding which holds the positive ions together. These electrons are not localized on any atom but rather delocalized uniformly over the entire crystal. These free and mobile electrons make metallic solids good conductors of electricity and heat. The electrons flow through a network of positive ions when an electric field is applied. Similarly, when heat is applied to one corner of metallic solid, the free electrons spread the thermal energy evenly throughout the unit. The presence of free electrons also accounts for the luster and color in some cases. Metals are highly malleable and ductile. Metallic solids have fairly high melting and boiling points. The other type of crystalline solid is covalent or network solids. The constituent particles in these solids are atoms. These atoms are held together in large networks by covalent bonds. This interlocking network of covalent bonds extends throughout the crystals in all directions. Hence, covalent solids are also called network solids. They are also termed as giant molecules. Diamond, graphite and quartz are some network solids. As the atoms are held by strong covalent bonds, the solids are very hard and possess very high melting points. These solids are non-conductors of electricity, except for graphite.